So in this section, we are going to talk about jet transforms. So before this, we have seen Laplace transforms. So Laplace transforms are applicable for continuous time signals. So whereas jet transforms, we will be applying it for discrete time signals. Okay. So in our previous classes, we have already seen Fourier transform and discrete time Fourier transform. So discrete time Fourier transform. So we can write it as x of omega is equal to sigma n is equal to minus infinity to infinity x of n e power minus j omega n. So this is discrete time Fourier transform. So in Z transform, we are going to take Z as R into e power j omega. So we are going to write the Z transform x of Z as sigma n from minus infinity to infinity x of n into Z power minus n. So here R is the radius of the circle. Okay, so normally if I take Z is equal to R into e power j omega, so then what happens? I'll be getting x of n into R into e power j omega power minus n. Okay, so I'll be getting it like this. I'll be getting this as sigma minus infinity to infinity x of n into, if I substitute z is equal to r into e power j omega, then I'll be getting r into e power j omega power minus n. So this is equal to sigma from minus infinity to infinity x of n into r power minus n multiplied by e power minus j omega n. So this is same as the formula for discrete time Fourier transform. But only thing, instead of x of n, so instead of x of n over here, I have, so yes, instead of x of n here I have x of n into r power minus n. So discrete time Fourier transform can be applied to those signals which are absolutely summable. So sigma of x of n should not become infinity. So such signals. So some signals which are summable, which tends to infinity, so you cannot find discrete time Fourier transform for that. So for such signals also we can use Z transform. So why? Because we are multiplying r power minus 1 with x of n and then finding the discrete time Fourier transform. So that is why x of z in Z transforms is given as sigma x of n z power minus n. Okay. So let us go for Z transforms of some commonly used sequences. Z transforms of commonly used sequences. So the first one, unit sample sequence. So that is x of n is equal to del of n, or else, so I will be just writing unit sample sequence del of n. So I require Z transform of del of n. So how can we find Z transform of del of n? So as in the case of Laplace transforms, we have unilateral Laplace transforms and bilateral Laplace transforms. So in the same way, Z transforms also we can categorize them as unilateral and bilateral. So I'll be taking the limits only from 0 to infinity instead of minus infinity to plus infinity. Of course, all the sequences that I take now, so they will be present only for n greater than 0. So you know the meaning of del of n. So del of n means it is going to be 1 for n is equal to 0 and it is 0 for all other values of n if n not equal to 0. So the transform of del of n means sigma n is equal to 0 to infinity del of n into z power minus n. So this is equal to del of 0 into z power minus 0 plus del of 1 into z power minus 1 plus del of 2 into z power minus 2, so on. So del of n is equal to 1 for n is equal to 0. For all other cases, it is equal to 0. Therefore, I'll be getting del of 0 is 1 into z power minus 0 is 1. And for all the remaining, it will be zeros. So I'll be getting it as 1. So therefore, Z transform of del of n is equal to 1 for all values of Z. Okay. So next. So next sequence. Unit step sequence. So we'll be going for unit step sequence. So what is unit step sequence? U of n. So we know that U of n is equal to 1 for n greater than or equal to 0 and it is equal to 0 for n less than 0. So that is the meaning of unit step sequence. So Z transform of unit step sequence U of n is equal to, so same formula, 0 to infinity U of n into Z power minus n. So for n is equal to 0 to infinity, U of n will be 1. So I'll be getting 1 into Z power minus 0 plus 1 into Z power minus 1 plus 1 into Z power minus 2 plus 1 into Z power minus 3 plus so. Okay. So we have already seen or know that geometric progression. So sum of infinite terms, I'll be getting it as 1 by 1 minus Z inverse. If Z inverse is less than 1 for Z power minus 1 less than 1. Okay, so if Z power minus 1 is negative, sorry, is a fraction, then only I can apply this geometric progression. So therefore, I can write Z transform of U of n is equal to 1 by 1 minus Z inverse, or else I can write this as Z by Z minus 1. So here ROC is, I can apply it only for Z inverse less than 1, or else I can write it as Z greater than 1. So ROC is, so the magnitude of Z greater than 1. So that is for unit step. Okay. So next. The next sequence. So let us take unit ramp sequence. So unit ramp sequence means normally we call it as R of n, or that is equal to n into U of n. Okay, so that means R of n is equal to n for n greater than or equal to 0 and 0 for n less than 0. So Z transform of R of n is equal to sigma 0 to infinity, sorry, R of n into Z power minus n. So that is equal to sigma 0 to infinity. R of n means n for n is equal to 0 to infinity Z power minus n. So if n is equal to 0, it will be 0. If n is equal to 1, 1 into Z power minus 1. N is equal to 2, 2 into Z power minus 2. N is equal to 3, it will be 3 into Z power minus 3, plus so on up to infinity. So I can write this as Z inverse into 1 plus 1 plus 2 into Z inverse plus 3 into Z power minus 2 plus so on. Okay, so this is Z inverse into 1 by 1 minus Z inverse square. 1 plus 2 Z inverse plus 3 Z power minus 2 plus so on. I can write it as already you know, so 1 by 1 minus Z inverse square. So I can write this as Z by Z minus 1 square. Okay, if I substitute Z inverse is equal to 1 by Z, so you can write it as Z by Z minus 1 square. So for this also, the condition is Z power minus 1 should be less than 1, which implies Z should be greater than 1. So therefore, Z transform of R of n can be written as Z inverse by 1 minus Z inverse whole square, or Z by Z minus 1 whole square, where ROC is Z greater than 1. So the next sequence, so let us take an exponential sequence, that is e power minus j omega n into u of n. So which implies it is equal to e power minus j omega n for n greater than or equal to 0 and 0 for n less than 0. Okay, so Z transform of e power minus j omega n u of n is equal to sigma n from 0 to infinity your x of n, that is e power minus j omega n into u of n, multiplied by z power minus n. So this is equal to sigma n is equal to 0 to infinity. So I will be writing this as z power minus 1. Okay, e power minus j omega. I will be taking n outside the power. So z power minus 1 e power minus j omega whole power n. So I can explain this as if n is equal to 0, it will be 1. If n is equal to 1, z power minus 1 e power minus j omega. If n is equal to 2, z power minus 1 e power minus j omega whole square plus so on. Okay, so I can write this as 1 by, so 1 plus a square so on till infinity, 1 by 1 minus a. So I can write this as 1 by 1 minus z inverse into e power minus j omega. So mod of e power minus j omega is 1. So for this, Also the condition is Z inverse less than 1. Okay, so I can also write this as, if I write Z as 1 by Z, so we can write it as Z by Z minus e power minus j omega. Okay, so therefore e power minus j omega n u of n. Z transform is, I can write either as 1 by 1 minus Z inverse e power minus j omega, or else I can write it as Z by Z minus e power minus j omega. So ROC is same, mod Z should be greater than 1. Okay, so next signal might be the fifth one. Sinusoidal sequence. So that is sine omega n into u of n. Call it as symmetry. So Z transform of sine omega n u of n is equal to sigma n from 0 to infinity sine omega n into Z power minus n. So we know I can write sine theta as e power j theta minus e power minus j theta by 2z. So I'll be writing this as sigma n from 0 to infinity e power j omega n minus e power minus j omega n by 2j multiplied by z power minus n. So I can write this as sigma n is equal to 0 to infinity. So as like the previous case, z power minus 1 into e power j omega power n minus z power minus 1 into e power minus j omega power n all divided by 2j. Okay, so I can write it as two summations 1 by 2j sigma 0 to infinity z power minus 1 e power j omega power n minus sigma 0 to infinity z power minus 1 e power minus j omega power n. So I can write this as same 1 by 2j into, so this is 1 by 1 minus z inverse into e power j omega, and the second one will be 1 by 1 minus z power minus 1 into e power minus j omega. So simplifying it or writing it in terms of z, 1 by 2j into z by z minus e power j omega minus z by z minus e power minus j omega. So I'll be getting this as 1 by 2j into z into z minus e power minus j omega minus z into z minus, no, both, this is e power j omega, z minus e power j omega by z minus e power j omega into z minus e power minus j omega. Okay, so this is 1 by 2j. So this is z square and minus z square gets cancelled. So minus z into e power minus j omega minus 1 plus z into e power j omega. So I can write this as z into plus e power j omega minus e power minus j omega divided by z into z, z square minus z into e power j omega plus e power minus j omega. So multiply the two fractions plus e power j omega into e power minus j omega. So that becomes 1. So the numerator e power j omega minus e power minus j omega. So if I divide it with 2j, I'll be getting it as sine omega. So the numerator becomes sine omega divided by z square minus e power j omega plus e power minus j omega. So we can write it as 2 into cos omega. So this becomes minus 2 z cos omega plus 1. Okay. So we can write sine omega n multiplied by u of n. So its z transform is z into sine omega by z square minus 2z cos omega plus 1. So ROC, as our previous derivation, z mod z should be greater than 1. Okay. So in the same way, we can also go for sinusoidal sequence. So x of n, x of n is equal to cos omega n into u of n. So z transform of cos omega n into u of n is equal to similar derivation as we have done previously, cos omega n into z power minus 1. So I can write cos omega n as e power j omega n plus e power minus j omega n by 2 multiplied by z power minus n. So I can write this as 1 by 2 sigma n from 0 to infinity z power minus 1 e power j omega power n. Okay, plus sigma n is equal to 0 to infinity z power minus 1 e power minus j omega power n. So as like the sinusoidal, we can also write this. So 1 by 2 into 1 by 1 minus z inverse into e power j omega plus 1 by 1 minus z inverse into e power minus j omega. So 1 by 2 into, if I multiply and divide with z, z by z minus e power j omega, z by z minus e power minus j omega. So similar derivation, 1 by 2 into z into z minus e power minus j omega plus z into z minus e power plus j omega by z minus e power j omega into z minus e power minus j omega. So I can write this as 1 by 2. So z square plus z square, I will be getting 2 into z square, 2 into z square. Okay. Next, z into e power minus j omega minus z into e power minus j omega minus z into e power j omega. So I'll be getting it as minus z into e power j omega plus e power minus j omega. Okay, divided by same denominator as your sinusoidal, z square minus z into e power j omega plus e power minus j omega plus 1. Okay, 2z square. So I can write this as, so if 2 and 2 gets cancelled, so I'll be getting this as, so if I take z common, z into 1z will be there, 2 gets cancelled, minus, so I have taken z common, so e power j omega plus e power minus j omega by 2 divided by, so as like our previous one, z square minus 2z into e power j omega plus e power minus j omega by 2 plus 1. So I can write this as z into z minus cos omega by z square minus 2z cos omega plus 1. Or else if I want it in terms of z power minus 1, then I can write it as 1 minus z inverse into cos omega by 1 minus 2 into z inverse into cos omega plus z power minus 2. Okay, so divide the numerator and denominator with z square, you will be getting that. So here also the condition is mod z greater than 1. Therefore, cos omega n u of n. So its z transform is z minus cos omega by z square minus 2z cos omega plus 1. ROC z greater than 1. Okay, so hope all these are clear. So in the next session, so we will be going for the properties of z transform and also z transforms of some basic signals. So let us do some or find z transform of some basic signals. So find z transform of the following. So we have already seen del of n. So z transform of del of n is 1. Okay. So let us find out z transform of n into del of n. So n into del of n. So what will be the z transform? So let us find. So sigma n is equal to minus infinity to infinity x of n into z power minus. So in this case, x of n is n into del of n multiplied by z power minus n. So we know that del of n is equal to del of n is equal to 1 for n is equal to 0, and it is equal to 0 for n not equal to 0. So if n is equal to minus infinity to minus 1, del of n will be 0. For n from 1 to infinity, del of n will be 0. So den of n will be 1 only when n is equal to 1. But when n is equal to 1, sorry, 0. N is equal to 0, so 0 into, or let us write completely. So minus infinity into del of minus infinity into z power minus or minus infinity minus so on till if n is equal to minus 1, n is minus 1, so minus 1 into del of minus 1 into z power 1 plus if n is equal to 0, 0 into del of 0 into z power minus 0. If n is equal to 1, 1 into del of 1 into z power minus 1 plus so on till if n is equal to infinity, infinity into del of infinity into z power minus infinity. Okay. So here del of minus infinity is 0, so on till del of minus 1 is 0. Del of 1 0, del of 2 0, so on till del of infinity is 0. And for this term n is 0. So therefore I will be getting 0. So for n into del of n, the z transform is 0. Okay. So in the same way, so suppose I want to find z transform of del of n minus 3. So I can write it as sigma 0 to infinity or minus infinity to infinity. So anything is the same. Okay. Del of n minus 3 into z power minus 1. So we know that del of n minus 3 will be equal to 1 for n is equal to 3 and it is 0 for all other values of n. So I will be getting it as 1 into z power minus 3. Okay, because for all other values it will be 0. Only when n is equal to 3, I will be getting del of 0. And for all other values, del will be 0. Okay. So I will be getting this as z power minus 3. Therefore, del of n minus 3, z transform is going to be z power minus 3. So del of n minus n naught, I can write del of n minus n naught, the z transform is z power minus n naught. So in the same way, by combining the above two questions, if I want to find z transform of n into del of n minus 2, suppose I want to find z transform of n into del of n minus 2. So I'll be getting n is equal to minus infinity to infinity n into del of n minus 2 multiplied by z power minus n. So this is going to be equal to 1. So del will be going to be equal to 1 only when n is equal to 2. So let me write del of n minus 2 is equal to 1 for n is equal to 2. For all other values of n, it is going to be 0. So if n is equal to 2, I will be getting 2 into del of 0 into z power minus 2. So I will be getting it as 2 into, sorry, z power minus 2. 2 into z power minus 2. Okay. So n into del of n minus 2. The z transform is going to be 2 into z power minus 2. So in the same way, n into del of n minus n naught. So the z transform will be, isn't it, n minus n naught. So the z transform will be n naught into z power minus n naught. Okay. So next. So if I want to find out, so shifting in your signal. So I want to find out Z transform of x of n minus 1 into u of n. Z transform of x of n minus 1 into u of n. So what will I get? So that is equal to sigma n is equal to 0 to infinity x of n minus 1 into z power minus n. So let n minus 1 is equal to some k. So then n will be equal to k plus 1. So then I'll be getting this as sigma. So if n is equal to 0, k will be equal to minus 1. So until if n is equal to infinity, k will also become infinity. To x of n minus 1, I can write it as k. Z power minus n. So instead of n, I can write it as k plus 1. Okay. So this one, so z power minus k plus 1. I can write it as z power minus k into z power minus 1. So I can write this as z power minus 1 sigma minus 1 to infinity x of k z power minus k. Okay. So my summation should be from 0 to infinity. So if I want to write it as x of z. So for that what we will be doing? I will be writing this as, so if k is equal to minus 1, I will be getting x of minus 1 into z power minus or minus 1 plus summation k is equal to 0 to infinity x of k z power minus k. Is that okay? So summation k is equal to minus 1 to infinity. So minus 1 term I am writing it separately, and the remaining summation I will be having it from 0 to infinity. So this will be z inverse x of minus 1 into z plus z inverse sigma k is equal to 0. So this sigma k is equal to 0 to infinity x of k z power minus k is nothing but x of z, z transform of x of n. So z power minus 1 into z is 1. So I can write this as z power minus 1 into x of z plus x of minus 1. Okay, so therefore I can write, so what did we find? X of n minus 1 into u of n. So its z transform is z inverse into x of z plus x of minus 1. So in the same way, I can also find z transform of x of n plus 1, for example, into u of n. You can also find it as z into x of z minus z into x of 0. Okay, that is the z transform x of n plus 1 into u of n. X of n plus 1, or else let us do one thing. I'll also do this for you. Okay, one x of n plus 1 into u of z transform of x of n plus 1 into u of n. I can write this as sigma n is equal to 0 to infinity x of n plus 1 Z power minus n. So as in the previous case, I'll suppose n plus 1 is equal to k, that is n is equal to k minus 1. So therefore I can write the Z transform as sigma k is equal to, so if n is 0, k becomes 1. So if n is equal to infinity, k is infinity, x of k Z power minus k minus 1. So Z power minus k minus 1, I can write it as Z power minus k into Z power minus of minus 1. So that is Z power minus k into Z. So I'll be writing this as Z into sigma 1 to infinity x of k Z power minus k. Okay, so again the summation should be from 0 to infinity. So what I'll be doing, I'll be adding a term 0 and subtracting a term 0. So k is 1 to infinity, I'll be writing this as k is from 0 to infinity, x of k z power minus k. So I have added a term with k is equal to 0 to infinity. So I'll be subtracting a term with k is equal to 0. So subtracting a term k is equal to 0. So x of 0 z power minus 0. So z into sigma k is equal to 0 to infinity x of k z power minus k minus z power 0 is 1, so this I can write it as z into x of 0. I'll be dividing the z. So this is z into x of z minus z into x of 0. So as like I have previously said, I can write x of n plus 1 into u of n, its z transform will be z into x of z minus z into small x of 0. Okay, so in the similar way, for small signals we can find out the z transform quite easily. So in the next class we will be going for properties of z transform. Okay, so thank you for this.